आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़, की आवाज़।
Vigyan Ki Awaaz podcast series aims to popularize new ideas of science and technology, which highlight STEM, science, technology, engineering, mathematics, and medicine. This brings to the surface the efforts and researches of Indian scientists, which is desired to bring a change in community learning and teaching, access to knowledge of resources, and social paradigms. Our goal is to spread the name of indigenous Indian research stories and their masters among the masses of society in a very easy manner. Bose Institute was set up in 1917 by Sir Jagadish Chandra Bose, the founder of modern science in the Indian subcontinent. It is Asia's first modern research center devoted to interdisciplinary research and bears a century-old tradition. The institute was founded as not merely a laboratory but a temple, with its principal aims being the advancement of science and diffusion of knowledge. Swami Vivekananda, Sister Nivedita, whose influence is reflected in the institute's emblem of Vajra, was significant in the setting up of the institute, and Rabindranath Tagore were among those who had consistently inspired and supported Jagadish Chandra Bose in his endeavors. Ever since the establishment of the Department of Science and Technology, Government of India in May 1971, Bose Institute has been an autonomous grant-in-aid institution of DST. Over the last century, the institute has endlessly strived to preserve the legacy of its illustrious founder. In this podcast, we are happy to present Dr. Basudeb Maji, Assistant Professor in the Department of Biological Sciences in Bose Institute. He is trying to combine chemistry and biology to find out new avenues in the field of his research work. But before going into more details about his research work, let us hear from his own voice about his academic journey.
I am Basudeb Maji, and I am a chemical biologist here working at Bose Institute. So I did my PhD from Indian Institute of Science, IISc Bangalore, and then I worked at Harvard Medical School and MIT for 5 years, and then I started my own lab, and it's been 3 years now. But here at Bose Institute, I am working for last 1 year. So as I mentioned, my research topic is on chemical biology, and it deals with disease biology, and I try to combine chemistry and biology for the development of new therapeutic avenues or interventions.
Dr. Maji speaks about his collaborators and how as a team they work.
We are 4 people in a group, myself and my 3 students, Sadia and Orpita, and we are trying to develop new therapeutic modalities for both infectious disease as well as genetic diseases.
Dr. Maji explains some of the challenging part of his research work.
So as I mentioned, I have 2 components in my research. One is the chemistry part, the other one is the biology. So if you think about in a chemical point of view, so in chemistry lab we develop different drug candidates, and it's really important to have chemical synthetic route or synthetic approach to develop drug candidates. But at the same time they're challenging because both of resource constraint and time constraint. That's where we want to exploit chemical biology approach to make it more fast track and to expedite the process. So now I'll focus on very important topic before I get into my own research work. That is, if you think about disease, it's kind of like war, fighting a war. And in war, nothing is static, everything is dynamic, be it the battlefield or the target. So everything is dynamic. Now, if you think about in the point of view of medicine, having an effective and powerful medicine might not be enough long run, because your target, your enemy is constantly changing with time. So we recently came across such scenario during COVID-19 infection, where different variants were evolving and they were able to escape various generations of vaccines. So it is very important to be prepared to take up those challenges and have a system or like a platform ready to develop new agents, new medicine, new drug candidates for new challenges. So with that, so what we are trying to do, we are trying to focus on mainly 2 topics. One is antimicrobial resistance, the other one is the genetic diseases. So I will get into antimicrobial resistance first. If you remember, penicillin was a magic drug, especially when it was discovered in the beginning. Now it doesn't work. Why so? Because we have exploited, misused and abused rather, such a way that now it doesn't have any activity. So now I will refer to the same word, dynamic. So our target is dynamic. The target or the pathogenic bacteria, infectious bacteria which we are targeting, they are changing over time, they are evolving. And over time, with the exposure of or misuse of antibiotics, they have become or turned into superbugs. They have become resistant. Now we need to have novel modalities to tackle them, to fight against these superbugs. So what we are trying to do, instead of synthesizing drug candidates one at a time, which takes almost like 2 to 3 weeks in the lab, we are trying to exploit bacteria themselves. We have engineered the bacteria in such a way that they will make the drug. Not only that, they will be integrated with AI, artificial intelligence, in such a way that they will select the drug molecule by themselves to kill themselves. So this engineered bacteria is going to synthesize the drug candidates for us, and they will select the most active drug molecule for us. Not only that, in a lab we take almost 2 to 3 weeks to develop one drug candidate. Now you can multiplex, that means these engineered bacteria, they can synthesize millions of drug candidates in parallel. So when a drug takes 3 weeks to make in the lab, these bacteria, they can make millions of drug candidates in an hour. Now you understand how rapid and how fast track these like development avenues are, or rather these high throughput systems are. So trying to exploit this kind of engineered microbes, engineered bacteria in developing drug candidates and apply them to fight antimicrobial resistance. Okay, so now as we understand, our fight is against bacteria, infectious bacteria are dynamic. So we need to have novel method. So antimicrobial agent, for example, antibiotics are not going to be enough. So what we are trying to develop, or what we are betting on, is enemy of the bacteria. Like us, we have both bacteria and virus as enemy. Similarly, bacteria, they also have their own enemy. They are called their virus. It's called phage, bacteriophage. Now we want to exploit bacteriophage to kill the bacteria. So basically it's making friendship with enemy's enemy. So we are trying to help bacteria's enemy to fight bacteria.
Dr. Maji explains the advantage of bacteriophage therapy.
Now there are various advantages of using these bacterial viruses or bacteriophages. They can be very selective against bacteria. They can be replicative. That means if you give one dose, you don't have to take any other doses. They are going to replicate themselves in our body, especially in the target of infection. So you don't have to take multiple doses. It's going to replicate at the site of infection. Not only that, they will have very minimum side effect and there will be less chance of resistance. So this is the reason we are focusing on bacteriophage therapy or phage therapy. The main challenge in this avenue is the resistance coming from the superbugs. They are already resistant, they are very powerful, these infectious bacteria. So what we have to do, we have to make them weak so that viruses, they can kill them. So we are developing drug candidates, small molecule candidates through this high throughput platform that I talked about, this through engineered microbe. So these small molecules will weaken the bacteria and then will apply these bacteriophages which can infect these infectious bacteria and kill them. So this is the new modalities that we are working on and developing so that we can fight these superbugs.
Dr. Basudeb Maji, along with his collaborators, is in search of new avenues for new therapeutic modalities.
In general, we have two major challenges. One is infectious disease, the other one is the genetic disease that we currently see that is in surge. So, for example, if you think about genetic diseases, it's kind of like cancer or diabetes, these are all genetic diseases. Now, we need to understand a little bit about genetic disease. We are kind of like a system and we run by program and these programs are encoded in our DNA. Now, if there is any fault in the DNA, that's gonna make the system non-functional. So, for example, there are multiple genetic diseases like I mentioned cancer and diabetes, genetic diseases like neuronal disease, etc. So, we have to, if you have to correct these genetic diseases, we have to get into very lower scale at the subcellular level, which is called DNA. Now, if you have to repair DNA, so currently we are focusing on or exploiting one bacterial adaptive immunity called CRISPR. This CRISPR, they are kind of like microsurgery, they can do microsurgery and correct DNA. And this correction can actually lead to, can actually help us fight these genetic diseases. I will give you an example by which you can understand how powerful this CRISPR technology is. In 2018, a couple in China, they approached a medical practitioner. They had special medical condition, they had HIV infection. Now, there is no way they can have a child which is not going to be infected by HIV. But the medical practitioner, scientist, he sketched out a plan and he planned a surgery. Again, it's a surgery at the genomic level so that you change the code of a genetic element and make them resistant, make the cells resistant against the infection. So, he removed a gene called CCR5 or deleted CCR5 in such a way that the progeny or the embryo is become resistant against HIV infection. And that is how he successfully actually was able to produce two babies through in vitro fertilization, and these babies are permanently resistant to HIV. So now you understand how powerful this CRISPR technology is. However, unfortunately, the scientist was jailed for 3 years. Why? Because he did not follow ethical procedure and he also was not following the kind of he was not taking care of the side effect. Because even though CRISPR is powerful, we do not know its side effect in long run. So it's not advisable to apply these kind of powerful technologies, especially when you want to make permanent change in our DNA.
Dr. Basudeb Maji explains how they are working on gene therapy.
We are trying to make the gene therapy safe. How? We want to develop chemical tools which can control these gene editing technologies. That means you can turn it off when you want. Let's say if something goes wrong, you have to have some kind of modality to stop it. So we are developing chemical methods which can actually turn it off and make it more safe. And this is how we are trying to develop precision gene therapy method for genetic diseases.
We are thankful to Dr. Basudeb Maji for providing us with his valuable time.